This is my senior computer team lecture on the Fischer-Heun range minimum query structure. My name is Stephen Huan, and today is April the 2nd, which is coincidentally the day before I was supposed to go. Um, this presentation is meant to be watched with the abridged lecture PDF, like while reading it, which can be found at that link, or alternatively either the abridged RMQ lecture or the full lecture. One of them is twice as long as the other. The definition of the range minimum query problem is given an array containing integers or, not integers, containing numbers with length n and two indices I and j, such that I is less than or equal to j. Find the smallest element between I and j inclusive on both ends, as in including I and including the number at I and including the number at j. Uh, the first thing we're going to do is we're going to modify this definition a bit to return the index k of the smallest element. As in, instead of returning the value of the numerical value of the smallest element, we're going to return the index at which it occurs. Note that using with a given k, we can obviously get the numerical value by just indexing the array at that position, but we can't do the reverse. As in, if we have two duplicate numbers, we don't know which index it came from. The notation I'll be using for runtime is going to be fg, where f represents the function of big O for the build time or the pre-processing time, and g represents the time for the query time. Because for a range minimum query, you might have some sort of initialization or setup cost, but to build some sort of structure. But afterwards, you also have to answer the multiple queries. So we're going to time those separately and maintain a build cost, which is represented by a function f, and a query cost, which is represented by a function g. So there are some algorithms that might immediately come to mind when thinking of the range minimum problem. For example, Fenwick trees, also known as binary index trees or bits, and segment trees. These structures have been covered numerous times by people in senior computer teams, so I won't go over them in any depth now. But the idea is that they can both do it. They can both do range minimum query. They can both do other things. They can maintain updates, and they can do it in logarithmic time, which is all pretty good structures, pretty good stuff for competitive programming. But the Fischer-Heun structure we're going to see has a more theoretical value. Let's put it that way. So we're going to go through a few extended examples. We're going to maintain the same array. So the array is going to be 5, 3, 4, 1, 2. So the first solution we might think of is dynamic programming. There are only n squared possible queries because I varies between 1 and n, and j has to be greater than or equal to I. So the number of possible queries is going to be, let's suppose I is 0, then j can take on any value between 0 and n. And then suppose that I is 1, then it's 1 less value. And if you add all of those up, you get n times n plus 1 over 2, which is, asymptotically n squared possible queries. So if there's only n squared possible queries, we could just pre-compute all of them. And the way we're going to do that is we're going to look at this idea. So we have an array here. We have this range and this range. And so the idea is that if we know the answer to 0 to 2, and we know the answer to 1 and 3, we can combine these two answers and get an answer for 0 to 3. Now, the reason this works is that minimum is like a union element, as in like the minimum on this and the minimum on this is the minimum of those two is going to equal the minimum of this. Keep in mind, this doesn't work for something like sum, because if we're trying to like find the sum of this range and we try to add up these two, we'd obviously overcount the intersection. But since we're thinking of minimum, we can just union them. And so one is going to start at, okay, so yeah. We're gonna build up our DP table here. These elements are grayed out because you can't have starting at 4 and going to 2 length. Yeah, this is starting index, this is the length of the range. So for a length of range 1, we're going to DP on the length of the range basically. For a length of range 1, there's only one element in each one, so it's just going to be the array basically written out again. 5, 3, 4, 1, 2, 5, 3, 4, 1, 2. Then for a length of range 2, what happens is that we're going to combine each of these as we discussed with this example. So 0 to 2 is going to be the min of 5 and 3, right, which is 3. So these two you can combine to form this answer. These two you combine to get this answer, the minimum 3 and 4 is 3. These two get to here, and this two get to here. We just keep on doing this. These two get you this one, these two get you this one, and these two get you this one. We can build up the entire table here, and once we have this table, to answer any given query, we just look, like for example, to go from here to here, this range is starting at 1, the index 1, and going for a length of 3, then we can just look at, okay, starting at 1, going for a length of 3, the answer is 1. And so using this approach, we compute n-squared elements, but we can answer any query in O of 1. The problem is n-squared is usually too big, usually too poor for like most competitive programming applications, and if n is greater than like 1,000, then it won't work out. So can we do better? And the answer is yes with sparse tables. The idea of sparse tables is that we don't actually need to compute every single n-squared range. We can answer the minimum query based off 2 pre-computed ranges. So the idea is that suppose we have this range of length 18. If we just break it up to ranges of length 16, we can just merge them together. Again, we're taking advantage of the fact that they're intersections. And in general, we can always break up a range into smaller ranges of a power of 2, because the nearest power of 2 is at least half of the size of the original one. So as in, if we can pre-compute for every starting index the power of 2 length, we can always take a general range and decompose its length into a power of 2 using 2 of them. So, to clear up the sort of theoretical things, it's going to look very similar to the DP table, except instead of, in squared values, our length of the range doubles every time because we're doing logarithmic stuff. So it goes from 1 to 2 to 4. So again, for a range of length 1, it's just going to be the array written down again. For range of length 2, in the DP we did adjacents, but in this case we're not doing adjacents since we're going to build it up, based off the powers of 2. So instead of doing adjacents, we're going to look at 0 to 1, and well, for this one, for the initial case, it's just going to be adjacents again because of how it works out. But if we look at this case, when it goes from these two to this, it's not, the adjacent minimum of 3 is obviously not 1. Instead, 0 to 2, to get the range from 0 to 4, you go from 0 to 2, and then you go from 2 to 2, and then that gets you 0 to 4. So if we look at 2 to 2, that's 1. And so we compare 3 and 1, we get 1. We compare this one and this one, and we get 1. And now we have the correct table. So it's very similar to dynamic programming, except dynamic programming uses the adjacent case. And in this case, we have to jump down and look at the power of 2 case down. So other than that, the major difference between the two is going to be query. If we're trying to do a query from index I to index j, then we're going to try to find a power of, we're going to try to find a number k such that 2 to the power of k is less than or equal to j minus I plus 1. Basically, we're trying to find the nearest power of k such that it, 2 of them will cover the entire range. Once we find that, then we can just, look at I to I plus 2 to the k, that like the half range basically, and then j minus 2 to the k to j. And if we take the minimum of those two unions, then we'll answer our range minimum query. So again, sparse tables, they do basically the exact same thing as a dynamic programming table, except one, we go from an n squared computational time to an n log n computational time, and 2, we still have the O of 1 or the constant time query because we can take a general range and decompose it into ranges of length powers of 2. This is very, very similar to the 2 to the n jump pointer idea for the lowest common ancestor problems, which I'll get to later. Now, let's look at a different approach, a pretty orthogonal approach to the last two we've seen. The idea is that we're going to break up the array into blocks. And so this is, this is some array. We took, actually, no, this is the sum array, like the 1, 1, 2, 3, 4, the 15 length array here, and we take a block size of b equals 3. That means that for every like group of 3 elements, we compute its minimum. Again, like this is a block, this is a block, this is a block, this is its minimum, this is its minimum, this is a minimum, and we get a subarray of length n over b because, that's how division works. We take something, we divide it into b blocks, we get n over b number. And so we can do this, we can compute these minima in O of n because they're n over blocks and cost O of b per block, so it's O of n to compute the minima for each block. Maybe you've heard of square root decomposition. Square root decomposition is basically a special case of this idea. So to see how we're going to use it for range minimum queries, we're going to look at so we have the blocks, we pre-compute the blocks, we pre-compute the minimum in each block, and then to answer a query, that's where our algorithm comes in. So case number 1, they're all in the same block. Well, so one of the arrows represents I, one of the arrows represents j. Case number 1, they're in the same block. All we need to do is just walk in the block and see what the minimum is, right? So that's O of B, right? Case number two, they're in different blocks, but they're in adjacent blocks. So all we need to do is walk from this one to the end of its block, so here to here, and this one to the beginning of its block, so there to there. And again, that's O of B because that's 2 blocks. Case number three, we need to take into account they're in different blocks and they're non-adjacent blocks, as in there's a block in the middle. Well, the idea here is that we can just do the same thing where we walk from here to its end, here to this end, but then we can, instead of going through all three of these, we can just look at the pre-computed minima. And to see how that saves time, if we go to the the extreme case where we're like here and here, again, we go from here to here, here to here, but then we can use 26, 23, 62 and take the min of these and walk over these instead of walking over, each particular element. So our query time is going to be O of, in the worst case, O of B, because we need to walk inside of the block sometimes, plus O of n over B, because we could walk over the tops of these blocks, which are n over B at most. And to minimize B plus n over B, because we want to minimize the query time, if you take the derivative of with respect to B, set it to 0, you get that B is the square root of it. This is where the square root of decomposition comes from. So we're going to generalize the idea of block decomposition into an idea called hybrid structures. For block decomposition, basically we did a naive minimum query where we just walked over each array, right? As in like the most naive algorithm, it has no pre-processing time, but it takes O of n per query because you have to look at each element. We basically did that for each subblock and for each summary block. So we're going to use different algorithms for the top and bottom blocks. For example, we might build a DEP table on each block level, but we might build a sparse table on this summary, on this so-called summary RMQ, because we're taking the summary, the block minima, and we're building another structure on top of that. So if we're working under this framework where we have some summary structure and then some block level questions, and we can answer by them by doing some sort of hybrid where we answer a block, and then answer for, and then use the summary to compute in the middle. We need to save time on basically building the structure because it takes a lot of computing time. So we find that some blocks are going to be similar to each other. As in if you look at these two arrays, one is 1, 3, 2, 4, the other is 10, 30, 20, 40. The arrays are obviously not equal because they contain different numbers, but they're similar in the sense that any range minimum query is going to have the same answer. This is well, you might ask me, wait, isn't range minimum query the minimum number? Well, no, we clarified that we redefine it to mean the minimum index. And and if we redefine it to be the minimum index, obviously this has the same minimum index for any query, for any RMQ query, as the two arrays. So we call the two arrays similar, which we'll denote by this little tilde. So now, and another thing is that our running time of the algorithm is now determined on how fast can we determine whether two blocks are similar or not, and how many different types of blocks are there. Suppose like there was only one block type. Obviously that's not true because that there just isn't. But suppose there was, then we would only need to build one block level structure as opposed to how many blocks there are, n over b. Okay, so we realized that the block structure, we can actually detect the block structure using Cartesian trees. So what is a Cartesian tree? It's a binary tree. This is the important properties. It's a binary tree, so each node has at most 2 children, but could have less, whose in-order traversal yields the original array, and which is a min heap. So min heap means that its parent is going to have a lower value than its children. Now, it's built on top of an array. That's the in-order traversal yields the original array condition. And the reason why these Cartesian trees correspond to our block types is that a block type, two arrays have the same block type if and only if they have isomorphic Cartesian trees. It's actually, fairly similar to proof. And by isomorphic, I mean same shape. If we prove in an if and only if, you basically have to prove each direction. If we prove the forward direction, as in if block 1 is similar to block 2, then they have isomorphic Cartesian trees. Well, our Cartesian tree is built basically, the root is going to be the minimum of the entire array, and then its left and right children are going to be the Cartesian trees of the subarrays. So if we see this, 3 is the minimum of the entire array, and its left child is going to be the Cartesian tree built on this subarray, and its right child is going to be the Cartesian tree built on this subarray. What I'm trying to say is that if the minimum at every position is the same, then it's going to build up the same Cartesian shape because the Cartesian tree is going to be built off the minima. And the other direction, the isomorphic Cartesian trees implies the block positions are the same. We realize we can answer range minimum queries using the Cartesian tree. If we do basically an in-order traversal of the Cartesian tree, and it basically corresponds to the lowest common ancestor between uh, two nodes in the tree, because the lowest common ancestor is guaranteed to be between them in the array, and it's guaranteed to be the lowest number, aka the range minimum. So what we're trying to say is that if two blocks have the same Cartesian tree, same shape Cartesian tree, that means that they must have the same range minimum query, since we can answer a range minimum query using the lowest common ancestor of the two nodes. Thus, being the same block type is, logically identical to having an isomorphic Cartesian tree. The question is, how do we quantify the shape of a Cartesian tree, and how do we build up these Cartesian trees? And we're going to do a sort of inductive algorithm. This is the idea. So, when I say inductive, I mean like we're going to take a Cartesian tree built on n-1 elements and extend it to be built on n elements. The Cartesian tree for one element is just the node itself, so that's the base case. And we have two conditions we need to maintain. The first condition is that it has to be a min heap. The second condition is that the in-order traversal has to yield the original array. To maintain the in-order traversal yielding the original array condition, we can just basically add it to the right side, because if we add it to the right side, then the in-order traversal will process at last, and the new node has to be the last one. So we're gonna add it to the right. We're gonna add it to the right side and have like the tree to its left or as its parent. And then to keep the min heap property, we can only add new children. If we have a new element, we can only have its parent be less than it, the value of the parent, obviously, to make it a min heap. So this is our algorithm. We have a stack of active nodes, or nodes on the spline of the tree, basically. To insert a new node, while the stack is not empty and the top node is greater, as in like we need to maintain the min heap property, so the top node has to be less than, because we're gonna take this new node and we're gonna make it a child of this top node. So the top node, for this new node to be a child of the top node and for it to be a min heap, the top node has to have a value less than it. And so while it's greater, we pop nodes off the stack because they can't be the parent. Finally, once this condition is done, we make the parent of the new node the top of the stack at the top node, which guaranteed has a value less than it, or if there's if the stack is empty, because the stack can empty out before we find such a node. Basically the new node is now the root, which is fine. We make the left child the last node that was popped off, as in we've been popping nodes off the stack. The last node we have the node on top of the stack, and the last node popped off the stack. If nothing was popped out, then it's just nothing. It doesn't have a left child. But otherwise, we make it the left child, and then we add this new node to our current stack. While it sounds like there's two loops here, for each node, for each number in the array, while there's two loops that might sound like n squared. What we realize is that a node enters. What we realize is that the number of operations this algorithm does is bounded by the operations of the stack, which will come important later. And we realize that the node, at most enters the stack once and exits the stack once. So, it does at most 2n operations because it enters the stack and exits the stack. And so obviously it runs an O of n if it does 2n operations. And in order to detect whether two blocks are isomorphic, again, that was the entire point of these Cartesian trees, we're trying to see whether two blocks are the same. In order to see whether two Cartesian trees are the same, we realize that it's determined by what operations we did to the stack. So we're going to call a push to the stack 1, a pop to the stack 0, and the resulting binary number we get we'll call the Cartesian tree number, which has a length at most 2n, since there's at most 2n push or pop operations. And obviously it's at most 2n operations, so it could be less than, so we might just pad it with extra zeros if it's less than 2n. But what happens is that we get a new number that's determined by the pushing and popping of the stack, which also determines the shape of the tree, since if it has the same pushes and pops, then this algorithm builds Cartesian trees and must have the same shape Cartesian tree. So instead of, comparing the shape of the Cartesian trees, we'll compare the numbers, which is basically like a simplified version of the shape. And there's only 2 to the 2 in numbers there could be, which corresponds to 4 to the n possible Cartesian trees for a given array of size n. Well, this is actually an upper bound. The actual number is determined by Catalan numbers, which I won't go into, but basically it's smaller. This is an upper bound. The actual number is lower than it, which is even better for our algorithm. So if we look at this observation of Cartesian trees and what it does for our runtime, we're going to use a sparse table. Again, the in log n structure, the in log n time build structure that we discussed earlier on the summary array, as in our Harvard structure, the top one, and a brute force DP, full computation on each block level structure. So the running time of this is going to be n over b. This is the build time. The query time is going to be O of 1, since the sparse table does an O of 1 query and the DP table does an O of 1 query as well. So it's going to be so the query time is going to be O of 1 no matter like these things. So it's O of n because we have to look over the array, build the blocks up. That takes O of n time to generate the summary array. If you remember the argument n over b times b, it's going to be n over b log n over b technically, but we'll discard the n over b factor. This is for the sparse array because the summary array has a size of n over b for block size b, and it takes n log n, which means it runs in n over b log n over b, plus the number of distinct blocks times b squared. Note that it's not note that the number of distinct blocks is not n over b, because as we argued before, if the number of okay, well, put it this way, there are n over b blocks, but the number of distinct blocks is going to be less than that because not every block is going to be a distinct Cartesian tree. Not every block is going to be going to be different. So we only need to compute the blocks which are different, as in if we have a block that we already computed a DP table on, and we have another block which has the same answer to the range minimum query as that block, we can just reuse the same DP table. We don't need to build a new table ourselves. And of course, the DP table takes n squared time, so it's going to be b squared. We know that there are 4 to the b distinct blocks from our Cartesian tree argument, so that just simplifies. And then from here, we realize that we need to pick b. Okay, so at this point, we need to pick a value for b. B is a block size. It's some parameter we can determine ourselves. And so if we pick b is greater than log n, the 4 to the b factor grows exponentially. So this will, basically, sparse tables already do n log n build time O of 1 query. So we're trying to beat n log n. We can't get something exponential. We need something linear, like O of n. So we need b to be less than log n. And then we can't have b be as small as possible because then this term grows to infinity if b is like 0 or something. So we need something between 0 and log n for b. And so if we say b is in the form, some parameter k times log n, where log is base 4, because 4 to the b, then we get this is still n, since the b is now in the form log n, so the log n's cancel, so you get n plus, and then doing some log math, 4 to the power of log 4k becomes n to the k. This becomes k log 4n, and so we get that it's O of n plus n to the k times k log 4n squared. Now, what we want is that, the idea is that we're going to skip the math here. The idea is that log is going to always be bounded by a polynomial, no matter how small the degree of the polynomial. It's sort of counterintuitive, but like log to the power of 100 is, big O, n to the power of like 0.00001. What I'm trying to say is that every polynomial asymptotically dominates every single logarithmic function. So to make this linear, all we need to do is pick a k less than 1. Because if k is less than 1, then this log factor basically, doesn't matter. This will be linear time. This will be O of n time. So all we need to do is pick k somewhere between 0 and 1. So, why not, if k is between 0 and 1, why not 1/2? Safe pick that guarantees that this runs in linear time. So, in summary, this is called the Fischer-Heun structure. We set the block size to a multiple of the log base 4 of the size of the array, usually k equals 1/2. We split the array into those blocks and we calculate the minimum in each block as discussed before. We build a sparse table on the reduced one, as in the n over b size one. We build DP tables on each block, reusing the structure if it has the same Cartesian tree number, and we answer using queries using this usual hybrid approach we discussed earlier. So this is what it looks like. Again, we have this array with 4 blocks. We compute the summary RMQ, or the minimum of each, the minimum number in each block, and we built a sparse table on this one, which is going to run in O of n time because the sparse table is n log n, and this is n over log n size. And then for each block, we compute its Cartesian tree number, which we discussed how to do that earlier. We know that there are only 4 to the b possible ones, which bounds the number of brute force DP tables we make. And for each block, if 2 blocks have the same Cartesian tree number, we don't need to, basically we associate Cartesian tree numbers with DP tables, and if 2 nodes have the same Cartesian tree number, we don't need to make a new DP table for them. So now that we've heard about Fischer-Heun, it's how it works, and the fact that the running time is O of n construction, O of 1 query, which is ridiculous, theoretically optimal. Sparse seg trees, bits, they run in like n log n, or O of n construction log n query. They don't hold a candle to O of n, O of 1 query. O of n construction, O of 1 query. So some sample problems. Spodge range minimum query. I don't know what the SCT stands for. It's just a direct application of RMQ. All it is to give you an array, to give you some queries, and you answer range minimum queries. I'd recommend I like to, when I first implement an algorithm to make sure it works, I like to just test it on these sorts of problems. There's no complexity to it. It's just does it work or not. And we'll talk about more general applications here. The idea is that you can take use-to-kill max flow, or any LCA lowest common ancestor problem. Use-to-kill max flow is not a max flow problem. It's kind of a misnomer. The idea is that we're gonna take a tree, an arbitrary tree, and then decompose it into an array using a Euro-Layer Tor. Euro-Layer Tor is basically a pre-order traversal and then a post-order traversal that gets you a list of nodes. Yeah, that's not very specific, but it's the idea of like taking a pencil and then going at like the root and then like drawing it to each of the children without ever like lifting up the pencil, and then like the order you get when you do that, it's basically Euro-Layer Tor. It's a traversal where you visit every edge exactly once. But yeah, I'm not exactly going to go into detail about that. But basically, if you do this traversal, you get a resulting list, and then the idea is that in that list, if you have 2 nodes, the LCA must be between those 2 nodes, because when you're processing it, when you're generating up the list, you visit the LCA between them, and so. And the LCA obviously is the lowest node in the middle between them. What that adds up to is that the LCA is going to be the range minimum query of the height on the range minimum query on like a height array of like 2 nodes. So to find the lowest common ancestor between 2 nodes, you can instead do a Euro-Layer Tor, make an array of the heights of the Euro-Layer Tors, do the range minimum query problem, and then the index you get, you can correspond it to a node, and then you answer the problem. The last application, actually not the penultimate application, is there's a lot of problems you could do this on, but basically it's a string theoretic thing. We define the longest common prefix between 2 strings to be the longest common prefix. If you have ABCD and ABEF, the longest common prefix is AB, which has a length of 2. The LCP is the length of the prefix, basically. So basically in stringrooms, you have something called a suffix array, where a suffix array stores all the suffixes of a given string sorted lexicographically. A suffix of a string is just something starting as a certain angus and going to the end of the string, and sorted lexicographically just means string sorted alphabetically. So the thing about the suffix array is that it allows you to solve a lot of problems. It's pretty useful, but there's also something called a suffix tree. And so a suffix tree has way more structure. Like structure, like, like information, like literally like raw data, than a suffix array. So, and that's important because that allows you to do certain algorithms faster. So to, boost the suffix array, so to speak, and to give it more data, you construct what's called an LCP array, which is the value of LCP for each adjacent suffix in the suffix array. Now that's, useful and all, but it's only for adjacent suffixes. How do we generalize to the LCP between two, general suffixes? And the idea for that is that it's also the range minimum. Yeah, the argument is actually pretty simple. If the idea is that you can use like a squeeze theorem and then like basic. Okay, yeah. You can, if you want details, you can read the lectures, but the LCP value between two non-adjacent suffixes is going to be the range minimum of the LCP array, which again we define as the LCP value between adjacent suffixes. So that's very useful for certain strain algorithms. Yeah. Last usage, the most straightforward one is going to be to simulate like a sliding window or a monotonic queue or something like that. If I and j are the start and end positions of the window or queue, you can just do an arm queue, get the minimum element between I and j. So this is wrapping up, picking k. If you remember, we defined the block size for Fischer-Heun to be b equals k times log base 4 of the input size. So as I said, k equals 1/2 the standard pick. But if you do some experiments like this, you'll find that for pre-processing time, the minimum is actually somewhere around like k equals 1. And for query time, yeah, k equals 0.5 is at the bottom, but like if you look at the range here, it's not very much, and I'm pretty sure this is just like noise. Like it looks like a sine wave, but I think that's coincidental. So k equals 1 actually wins. The problem with k equals 1 is, theoretically speaking, your algorithm now runs in like n log n squared. So 0.8 maybe if you want to be a theoretical purist, but k equals 1, I think it performs empirically better, which is important if you want your algorithms to run in time. And yeah, this is important because on Usico Maxflow, I get like 12 out of 15 cases in Python using like a 2 to the n jump pointer implementation. Using Fischer-Heun with k equals 1/2, I get like 8 out of 15. And then using Fischer-Heun with k equals 1, I get 15 out of 15. So it actually does matter if you want to get like Usico cases or code forces or stuff like that. Sources, Stanford slides. These Stanford slides are great. I got basically all the information from them. And all the images came from that too, like, these images and stuff. Except for this one. This is my work. The lectures I mentioned on, LC, okay, so first of all, you can read my lectures. They go more into depth about everything, about LCA, about LCP, how they work. But, I also use a lot of SCT lectures. There's a lot of links, on binary index trees, on segment trees. These are a lot more practical and a lot more useful than, Fischer-Heun. They're used in a variety of situations, but there's also, stuff on lowest common ancestor. Yeah, this lecture was most similar to mine. Matthew Savage, 2015. Except he didn't go to Fischer-Heun. He basically stopped at Sparse Tables. There's an LCP lecture here. There's a lot of stuff. So that's it. Thanks, guys.